And okay, so now we're going to do the 20.4 rational functions. Okay, this is what we call rational functions. Actually, it's just like rational numbers, but now it's functions. Why? Because it's really like it's two sentences on in definition. We call a function that is the ratio of two polynomials a rational function. Simple as that. Before we have two real numbers, now we have two polynomials. And because polynomials have variables in it, and now it becomes a function, right? So it's just like everything we learned about real numbers in pre-algebra, things we do with numbers like dividing them, multiplying them, adding them, subtracting them, raising them to functions, everything applies here to, you can replace that number with a polynomial, a quote unquote an expression. So for example, like f of x equals to this monster of x plus 4, x squared, sorry, slanted plus 3. Okay, so this is a polynomial, this is a polynomial. This is actually a binomial, this is a trinomial, and a special type of polynomials, and this is what we call a rational function. Okay, we say it's rational because it's not irrational. What is irrational? It does not have the imaginary part. It's not a complex number. This is not complex. This is all it means. Okay, everything in the real real number realm is rational. Okay, so we have g of y equals to 2 minus y squared over y, and h of z equals to 3z fourth plus 2z cubed minus 1 and 6z plus 1. So you can see there it can have, more terms at the bottom, more terms at the top. You can have, a single term like a monomial. Either way works. As long as you have a ratio of two polynomials, it's a rational function. Okay, there are some manipulations we can do. Now we have the definition. So what we're gonna do now is trying to to solve something, right? Solve an equation. Now this is just a function. Once you have an equation, x over x minus 2 plus 3 over x minus, let's do slowly, 3 over x minus 5 equals to -1. Okay, now we have an equation equals to a number. It's an equation. If equals to f of x, that's a function. Okay, sometimes it's trivial things, right? But so when we solve this, how do we solve it? It's just like when we solve fractional problems, we find the common denominator. And the only thing we need to be careful is we don't have that extraneous roots. That's all there is. So for this one, we find the common denominator, which is just like the fractions. This is x minus 2, sorry, x minus 2 multiplied by x minus 5, x minus 5, okay, plus x minus 2, x minus 5. Oh, I really can't draw a straight line here. 3x minus 2, okay, equals to -1. So we have a common denominator. We have x squared minus 5x plus 3x minus 2 on top, right? At the bottom, it's the same thing. God, I really can't draw a straight line. X minus 2, x minus 5 equals to -1. Okay, now we multiply both sides by the denominator, right? So now we have x squared minus 2x minus 2. Okay, no, this is -1, so we have this equals to negative x squared minus 2x minus 5x plus 10. Okay, we move this over, so we have x squared minus 2x minus 2 plus x squared minus 7x plus 10 equals to 0. Okay, now we simplify by 2x squared minus 9x plus 8 equals to 0. Okay, now what we do is we can, now it just becomes a polynomial function, right? All right, so how do I end up with, oh, this is not minus 2, this is minus 6. There we go. That's where I got it wrong. Minus 6 plus 4. Okay, so now we have, that's why it does not. 2x minus 4. Sorry, 2x minus 1. X minus 1 and x minus 4. This is the factorization. I was talking about, we learned this. I'm not going to repeat it. So either way, this is polynomial function. You can try to solve it, and this will give you the roots of net x equals to 1/2 and x equals to 4. What you want to really make sure is to plug it back into the original equation so it works out. So it does not end up with a negative, or sorry, a 0 denominator. In this case, x is neither 2 or 5. It should be fine. So both of these roots are correct. But you should always double check. This is simple, straightforward enough. Like over here, we do have to check this each solution, make sure it doesn't make a denominator in the original problem equals to 0. So this one works. So both are roots. Okay, so makes sense. I'm going pretty quickly on this one. Let me do a check with everyone. Can you get either text something in the chat or give me a thumbs up? Thank you, Kevin. To let me know everything makes sense. Thank you, Gordon. Yo-Yo, you woke up yet? Yo-Yo, you here? How's your summer going, Yo-Yo? Seems like you have a pretty good summer. Oh, busy? Is that why it's bad? All right. Got it. That means a lot of work. Okay. Well, sometimes a fresh start actually might be a good thing. It's not fun when you start, but actually usually it's not as bad as you feared or imagined or worried about. Okay. Anywho, we have this okay. Okay, so let's go quickly on this one. So we have f of x equals to 3x minus 4, x over x plus 5. What is the domain of f of x? And graph the function, right? As x gets large, what value does f of x get closer to, right? So basically we're doing the graph. So in this case, first thing you need to note is x cannot be -5. Why? No 0 denominator. Okay. So since it's graphing, I am going to just look at the graph. Okay, so this is the graph of the function. So the way you can do it is you can plot out the field points and then connect them. So we're not going to spend time on that. So the domain really is x cannot be -5, everything else goes. So the domain is x, all real number except -5. Okay. So over here, you can see it becomes like this and it becomes like this. Okay. I'm not gonna get into it. This is like where usually an inverse function looks like, well, a real function, like a first order real function look like. Yeah, we're not gonna get into it. It's too what's the word? It's too big of a context for us to expand over right now. Okay, so over here it tells you how to graph it. What we can introduce is a horizontal asymptotic. Okay, what it means over here is x, since x cannot equals to -5, at this time y cannot equals to 3. Yeah, 3, right? So let's see. Sorry, yeah, x cannot over to so like y equals to 3 is because of this. So if you were to express x in terms of y, you cannot have this to be a 0 denominator either. So basically, so there are this like a two numbers for x and y. The graph will never reach. So therefore it becomes the shape of the graph. So this is called a horizontal asymptotic. Asymptote. Then this is a vertical asymptote, right? In Chinese, it's 渐近线. It's like you can approach infinite number of infinitely close, but you can never reach this number. Okay. Yeah, that's a whole chapter in itself, so I'm not gonna expand on that. So that's what you get for graphing it. Usually what you end up with is it's all real number except the number that makes the denominator 0. And the reason is when we have a rational function, you have terms at the denominator. Okay, so I'm gonna pass on that one. So 20.19, find the constant a and b such that 2x over x squared minus 5x plus 6 equals to a x minus 3 plus b x minus 2. Okay, so for all x except x cannot be 2 or 3, which is over here. Okay, find the constant that. So what we have over here is we find the common denominator, right? So this actually factor to x minus 3, x minus 2 nicely. So you can write this as ax minus 2 plus bx minus 3 over x minus 2, x minus 3. Okay, so we find the common denominator and we do this, right? So now the bottom is the same. So what actually can solve is 2x equals to ax minus 2a plus bx minus 3b. Okay, so this will be a plus bx minus 2a plus 3b. Make sense? So I expanded this ax minus 2a, bx minus 2b, and then I reorganized the term to have the same terms together. So x terms together, constant terms together. So what this tells me is the coefficient has to be the same. This one does not have a constant. What does it mean? It means it's plus 0. Okay, so now we have a plus b equals to 2, and 2a plus 3b equals to 0. Okay, makes sense? Okay, so now I have a set of functions, right? So a plus b equals to the term of this, and well, this in the book is negative. It doesn't matter because negative and positive is all 0. So this, I'm gonna just solve directly. Tells me b equals to 6. Sorry, b equals to -4, and a equals to 6. Yeah. Okay, so when you add the two, you have 2, and then when you do twice, this is 12, this is negative 12, it gets 0. So A equals to 6, B equals to negative 4. Okay, and this is how you solve this equation. Make sense? Okay. The other way we can do is we can just pick some value of x. We plug in x equals to say 1 or 0. Actually, 0 will make it much easier. If we have 0, then well, I guess we still need 2. We can pick x equals to 1 and 0, and then you end up with 2 equations and you can solve. You can solve the number, right? So either way, you have this as the solution. Okay. The factors in the denominator left side are same as the denominator, isn't an accent. A rational function with more than one linear factors in its denominator can be broken into a sum of rational functions with the linear factors are power in each denominator. This process of doing it is called partial fraction decomposition. What it means is over here, what you can do is you can write it in terms of this equals to that. You can write it in terms of each of the factor term, the decomposition. This is what it leads to. But that's again another whole topic in itself, so we're not going to expand that on that. So this is just like a taste of what other ways of functions can be created. Okay. In the interest of time, I'm trying to write about this chapter, so we are gonna move on to the piecewise piecewise defined function, which we already see. This is just more general. Like say, for example, the floor and ceiling functions we saw earlier. Sorry, not here. Are piecewise functions, right? But this is more like a piecewise defined function. What it means is the functional form is different depending on the value of the x. Okay. We do describe function as machine that takes an input and output according to some rule. Okay, the imagine we can also imagine it takes input but applies different rules, basically different to different inputs in order to produce an output, right? And we can call this piecewise defined function. And to describe such a function, we must give both the rules, right? So like this is a pretty straightforward function. I mean, a simple one. So f of x equals to 2x and 3x, depending on if x is less than 0 or if x is greater than 0. Note that it does not tell you what happens when x is 0. Okay, so you cannot just assume f of x equals to 0 because x equals to 0 is not part of the domain. That's something you have to, you can't just, oh, it's like if x is 0, both of them give you 0, then I say f of 0 equals to 0. This is not right because it's not part of the domain. Okay, so in this case, when we draw the picture, you have to be careful to carve it out, right? So let's see a couple of examples. I have 20 minutes, half the time left. I don't know if I'll be able to finish everything. I'll try. So we have f of x. This function is defined 3 pieces. X plus 5 when x is less or equals to -3. 2x squared minus 1, -3, and less or equals to 2, and negative x over 2 when x is greater than 2. Okay, so if I were to say f of 1, okay, where does 1 belong in this range? Then it's 2, 1 squared minus 1, so that's 1. F of 9, okay, 9 is the last one, so -9 over 2, so -4.5. I have f of -12. Oops. And 12 is in the first one, so -12. Negative 12 plus 5 equals to negative 7. You see, depending on the value of x, you pick a different rule to apply to the function. Right? Okay, so that's the first part. And what is f of f of f? I think it's 4 layers of f of negative 12. You're like, what? What is this? Again, when you see nesting, you just like peeling off the onions, you do one at a time, right? So f of negative 12, we know it's negative 7. So this is f of f of f of negative 7. So you just replace this whole thing with this value, negative 7. Yes? F of negative 7 is still less than that. So negative 7 plus a 5, which is negative 2. So you have f. You just remember each layer you peel off, you have one less f to work with, f of negative 2. F of negative 2 happens to be in this range. So 2 squared, 2 squared is, give you 8 minus 1, so that's f of 7. Okay, f of 7 is equals to negative 7 over 2, so negative 3.5. Okay, so when you see nesting, don't be afraid. It looks really ugly, terrible, but just one layer at a time. I'm not sure if I'm going too fast. Am I going too fast? Okay, so now the question comes up, for what value of x is f of x equals to x? Equals to x. Okay, so this is not a functional form, what I'm saying over here. It's like you're looking for a particular number when f of x equals to itself. Okay, so in order to solve that, what we can see is, okay, so if x, for the first part, can x plus 5 equals to 5 ever? This is not it's not possible, right? So this is not, it doesn't have a solution. So can x equals to negative x over 2? This is only when x equals to 0. Okay, yeah. So for this one, to be true, you almost have to have 5 equals to 0. So this is no solution, right? For the first range. For this one, only x equals to 0. However, in order for this to apply, x has to be greater than 2. So this is also no solution. Okay, because the solution does not fall into the domain of the function. So the only possibility left is 2x squared minus 1 equals to x. So this gives us 2x squared minus x minus 1 equals to 0. So that means 2x plus 1, x minus 1 equals to 0. Okay, so this gives us two solutions, x equals to negative 1 over 2, and x equals to 1. We plug it back in. If we have 1, you have 2 minus 1 minus 1 equals to 0. Okay, so we have this 2 multiplied by 1/4 is 1/2. 1/2 plus 1/2 minus negative 1/2 gives you 1. 1 minus 1 gives you 0. Both solution works. It appears, however, x also have to be between this range. Let's see if it is. Both numbers fall into this range. So for these two values, okay, for when x equals to negative 1/2 or x equals to 1, f of x equals to x. Make sense? So you have to be careful that you try each piece, make sure you look at the range, see if you have a solution. If it's the same within the range, within the domain, then that's the solution. If this happened to be, say, x equals to 3, that's outside the range, and that will not be a solution. But it doesn't. Okay. So does f of x have an inverse? Okay. For f of x to have an inverse function, f inverse of x, remember this? It has to be a one number in, one number out. But we can see in this range, because we have the square, so say, for example, x equals to 1, and then x equals to -1, gives you the same number, 2. Okay, so this portion will give you an inverse, this portion will give you an inverse because these two are also monotonic functions, but this is not. And it happens to pass through the part where you put 2 x's into the number, you get same y out, so it does not have an inverse. Okay, so if we were to graph it, you can see why. So yeah, like say, for example, right, in this middle range, it's not, you know, it's not unique. A y value are not unique, so you cannot have an inverse, right? Okay, so if we were to graph it, this is what it looks like. Okay, I'm not gonna graph it, but this is if you just graph 3 pieces and then cut it off at the appropriate range, you end up with the functions graph. Okay, so we use open circles to make sure we have the strict inequality or non-strict inequality to indicate what their what when x equals to the boundary, like say 2, which value to use. Okay, this graph is not continuous because you have all these breakpoints and that does not connect. Okay, we can draw a graph without lifting the pencil off the paper. So that's another concept, which in itself warrants a lot of discussion, but we're just like touching on it right now. Okay, I have 2 more problems to go. Let's see. So 20.21, write function f of x equals to square absolute value -3 minus 7x as a piecewise defined function without using absolute value sign. So absolute function actually is what we call actually is piecewise. So what happens is the value changes, f of x changes, depends on the value inside the absolute value sign. So let's see, when would this equals to 0? X equals to -3/7. Okay, x -3/7. So when this is, when x is greater or equals to, okay, I say when this f of x equals to 0. Okay, so when x is greater than -3.7, -3 minus 7x, let's see, will be greater than 0. Let's see if it's this greater than this. Actually, it will be less than 0, right? So if I pick -1 plugging, no, this is greater than 0. Sorry, -1 is less than it. If I pick 0, this is less than 0. Okay, if I plug in 0, it's less than 0. Sorry, momentarily brain freeze. If this is less than -3.7, then this whole -3.7x is greater than 0. Okay, so what happens is, what we can do, we can write this f of x equals to, when it's greater than 0, it's itself. -3, -7x, when x is when it's 0, it's also itself. So we can combine the 0 case with this less or equals to 3/7. 0 case we can actually combine with either one. So we'll just leave with the first term. If it's less than that, if it's greater than this whole thing is less than 0, so the result is negative that. So 3 plus 7x when x is greater than -3/7. Okay, so basically what absolute value function in its simplest form is equals to x when x is greater or equals to 0, negative x when x is less than 0. Okay, so this is just a transformation because it kind of moves, shifts, and stretches it. You get a different breakpoint, but either way, when you graph it, it becomes like something like yeah. I guess we'll say try simpler versions first. This is a way of figuring out the complex problem. So over here, you can see the solution, and they're trying out different versions of it by move it and shift it. Okay. All right, so 2022 actually happens to be this year. We'll end on it. We say a function f from the integers to integers is defined as follows. Okay, so note the domain of f of n is all integers, so it's not a continuous function. N plus 3. If n is odd, divide by 2 if n is even. Okay, so suppose k is odd. Okay, so now we have f of f of f of k, okay, equals to 27. So we're asked to solve for k. Okay, the function is pretty simple. We're just unless this whole like nested function, then we'll have an equation, then we can solve it. Okay, so let's start. K is odd. If k is odd, f of k equals to k plus 3. Okay, k is odd, this is odd number, then k plus 3 is even, so f of k plus 3 equals to k plus 3 divided by 2. Okay, now we run into a situation. If if k is say 1, then 1 plus 3 divided by 2 is 4. 4 divided by 2 is 2. That's an even number. If k is, say, 3, 3 plus 3 divided by 2 is 3. That's an odd number. So the next one, we have both situations. So we have f of k plus 3 over 2, or actually, so we have nest over layer number 1, 2, and 3, the other layer, equals to 27. Okay, so if this is odd, so then we have k plus 3 over 2 plus 3 equals to 27. If k plus 3 is odd. If k plus 3 is even, then we have k plus 3 divided by 4 equals to 27. Okay, so there we have two cases. Let's solve it. So in this one, we end up with k equals to 45. It is a odd number. Okay. So k is odd, and k plus 3 over 2 is 24. This is even. Okay, so actually this number needs to be odd in order for us to apply this rule. So even though k solve when we eventually solve for k is at 45, it's that fits the original original condition. However, in the interim term, we violate 24 is not out, so this is not a valid solution. Makes sense. Now we only have this case. We have k plus 3 over 4 equals to 27. So k plus 3 equals to 108. And k equals to 105. Okay. Okay, so okay. So k is 105. It's odd. Okay. So this is our solution. And k plus 3. So let's say our k plus 3 over 2 has to be even. So this is 108 divided by 2, which is 54, which is even. So both conditions, this is odd, both conditions are met. Okay, this is how I would solve it. Now I'm looking at the book. Since we have 1 more minute left, we can actually go through the book solution. The book solution goes backwards. It starts with this and going backwards, right? So it's not unnesting, it's actually solving this and going backwards. So there are two cases. If n, so we start with f of n equals to 27. Okay, so how would it end up with 27? If n is odd, then n plus 3 equals to 27. So that means n is 24, but n has to be odd. So this one does not work, similar to what we have over here. So case 1 does not work, right? So n has to be even. So then we have n divided by 2 equals to 27. Therefore, n equals to 54. Okay, so this is n54 is even. Okay, so then f of n equals to 54. We can go backwards again twice, right? And then we can unravel this. Now I run out of time. So basically it's saying you can go it from the inside out, you can go it from the outside in, either way. It's pretty similar